Okay, so to begin, we start by converting the PDF files we received from the city of Peterborough into GIS suitable imagery. To do so, we wrote a Python script, which can be seen here. So we set the workspace where the images are stored from Peterborough in PDF format. We set our output location, and then we use the ArcPy module PDF to TIFF conversion tool. Specifying the RGB to true color, which outputs the TIFF files as a 32-bit imagery. Once all the image tiles were converted to the TIFF format, we began to collect the needed metadata. So this metadata was collected mainly through the actual images themselves. So as can be seen here in this 1956 imagery, this is the first of the set. You can see here that the focal length was 152.14 millimeters, that the altitude above sea level was 6,750 feet. So those two, the focal length and the altitude, are two of the four that are mandatory for metadata. The other two are the coordinates for the center of each image and the physical paper dimensions. The physical paper dimensions were given to us by the city of Peterborough. Each of the image tiles themselves were 10 inches by 10 inches. The focal length and the flying altitude were captured from within the images themselves. To collect the center coordinates for the images, we use Google Maps, as you can see here, along with the image itself beside it. With the image beside it, we tried to find the center area of that image and then compare it to that area in Google Maps. And from that, we were able to gather the actual coordinates for that area. And then we stored them in an Excel sheet that we then saved as a tab delimited document. So as you can see here, we have the roll number, which was collected from the city of Peterborough from the actual photos that they had, the photo number, which was sent over in the PDF format, our actual naming convention of the images, the center latitude and longitude of the images, the focal length, the altitude, and then the height and width in inches, as well as the height and width in millimeters of the image tiles themselves. Once we had all that collected and we had saved it as a text file, we were then able to move forward into the HAP process, starting with the ingest step. So to access the HAP process, we open PCI Geomatica, select the HAP process there, and then go to ingest. So the raw images folder is just where we have all of our images for the set year that we're working with stored. So in this case, 1956, all the TIFF files are in all images there. The raw images metadata, which we had just finished collecting as the text file, and then we leave the fiducial options as corner, and then just specify where you would like that imagery to be output, in this case 1956, and just the ingest output folder. We're then able to run that. Once that is finished running, ingest step actually outputs the ingest folder here, as well as the ingest log, which just shows what actually took place in the ingest step, breaks down the flight lines that it's decided as well. What we need out of this is the .prj file here. We don't need the HAP process at this point, but we'll open up OrthoEngine and then bring the .prj file over into that. Once that is open, we then have to collect the fiducial points, which we can do so through the data input processing step. So we open it up, start with the first image, and as you can see here, all the fiducial marks have been collected for this image. Just to give you an idea of what you're looking at for that, it is just in the four corners. Once we've had all four of those collected for the first image of the set, we're then able to go ahead and run the auto fiducial collection. Once that's finished processing, you're left with this .rpt file here, which you can open up and view to see the number of fiducial points that have been collected. As you can see, most of them have the 4 there, but you get down to this area and some of them have the 3s or only 0, and that just happens when the images aren't clear enough at the fiducial areas. And then to fix that, we just had to go back in and manually collect the fiducial points. Then saving the .prj file again. And now we can go and do the nominal georeferencing step of the HAP software. Alright, so for the nominal georeferencing step, we open that up, browse to where the .prj file that was created out of the ingest step is stored. So in the ingest output folder right there, And then we also have to specify a reference DTM. In our case, we were able to clip a DEM of North America wide to the reference imagery, which we had received from the city of Peterborough, and were able to mosaic together. So here is the DEM here. And then finally, just specify a location where you want the nominal georeferencing to output to. Then we can run that. So once the nominal georeferencing step has finished processing, you're left with all these .pix files here. You can open those up into the focus window, and as you can see here, the images are now nominally georeferenced. So you can see that the river is flowing through there. Some of the roads are starting to line up here as well. So what we can do at this point is just doing a quick audit of the actual referencing. If we're happy with the results so far, we're now able to move on to the collection of ground control points and tie points. So to collect the ground control points and tie points, we actually used Ortho Engine, so we no longer are using the HAP software at this point. So once we have that open, we again just get the .prj file that was generated from the ingest step, bring that over, open it up in Ortho Engine. Once it is opened, we go to the GCP and TP collection and collect GCPs automatically. So we need to specify a reference image for the collection of the ground control points. So as I had previously mentioned, we did receive one in the forms of tiles from the city of Peterborough that we were able to mosaic together. So we select that, and then we also, for the elevation information, we again use that same DEM that we were able to use for the nominal georeferencing step. We left all the other parameters here as they were, and then we can run the match GCPs here. Once that process is done, we then add the GCPs to the project, and we can go and check to see how many have actually been added to the project. If it wasn't enough, what we are able to do is actually go back and run that process again, just with a lower minimum acceptance score. And what we did is, if we needed more, we would just lower that acceptance score by 0.05 each time. Then we move on to automatically collecting the tie points. Again, we just specified the DEM file that we've used prior in the nominal georeferencing as well as the ground control point collection. All the other parameters stay the same, and again, if we didn't get enough results for tie points on the first round of collecting them, we just lower the minimum acceptance score down to 0.05 each time until we get the required amount. Once we are happy with the amount collected, we can open the residual errors that you can see here, and we can start to delete any outlying residual scores here to lower the RMSs. So as you can see here, the RMS for the ground control points are 13.33 and 13.57. We are aiming for about 10 or lower, but based on the model and the output from the 1956 imagery, this was okay for that. As well, for the tie points, we are aiming for about a 1 RMS or lower. As you can see here, we have a 1.00 and 0.56, so that's perfect. Once we were happy with the residuals and the RMS scores, we're then able to move forward and actually generate an ortho images for each of the actual images we've created so far. So to do that, we just select all the images, put them all over into images to process. The DEM file is the same one that we've used prior throughout the process so far. We browse to an area where we want the orthos to be stored. In this case, again, the 1956 in the folder that we created called ortho. Select one of the files so that all the images as they become processed will go into that ortho folder. And then we specify that the automatic edge clip will clip 1%, as we found that created the best results in the mosaic step. And we can generate the orthos. Once that is finished, as you can see here, it's basically the same naming convention as we used prior, just with an O in front, symbolizing that it is an ortho. So with these orthos, that will be what we use for the mosaic step. So we just go into the mosaic, we define the mosaic area, just point out to where the actual mosaic will be stored, and then we go to the automatic mosaicing step here. All the images are being used in the mosaic, and we just go down to the selected method to edge features, and then we can go ahead and generate a preview. And then if you're happy with the preview, you can go ahead and generate a mosaic. And the final mosaic for the 1956 imagery looked like this. So as you can see, all the images are all as one now, mosaic together. All the roads are lining up nicely. And that's how we mosaic the images together.